Hi everyone. Today I want to talk to you about Azure Confidential Computing and more specifically offer you a high-level overview of the Confidential Containers project and how we can use it in Azure Kubernetes Service. Now, some time ago I gave a similar presentation on this subject. I said that confidential computing was a pretty complex subject, but fortunately though, Microsoft and its partners are really making a big effort to lower the barriers to entry regarding this subject. And as I suspected, confidential computing is becoming a lot more accessible, even for those of us who might have never heard about it. But before we get started, I'll introduce myself for a brief moment. My name is Thomas van Laere. I'm an independent Microsoft Azure consultant, and I help organizations, large and small, with lowering their operational costs through the Azure platform and through the use of open source technologies. So, what are we going to look at today? Well, I'll kick things off with a quick overview of the basics of confidential computing and why it might be an interesting option from an architectural point of view. There are definitely some cool benefits to jumping into it, but there's also a few things that you should be aware of. And once we've covered those bases, we'll dive into how confidential computing fits into an Azure Kubernetes setup. And yes, we'll be using the Confidential Containers project to really make the most of it. So my goal here is to clear up some of the mysteries that often surrounds confidential computing. Now, I'm not a big fan of filling slides with text, but there's a lot of nuance here that needs to be explained, so bear with me as we walk through it. So what does it mean to run a workload on Azure? You're putting quite a bit of trust in the cloud platform. You're not just placing trust in a bunch of different operational and technical processes, right? It's not just about trusting the people, the cloud operators and host admins, but also things like the hypervisor and other underlying systems. With so many layers involved, it's easy to see why people get concerned about privacy, control over their data, and security. For some businesses, these challenges can start to pile up, and until they're sorted out, certain applications just can't make the move to the cloud, and they'll be stuck on premises. Perhaps you've experienced this firsthand in your organization. Many organizations hit roadblocks when they run into strict data privacy and compliance requirements. This is a big deal in industries like finance and healthcare, where non-compliance can shut down entire projects. And then there's the issue of data control and sovereignty. Companies often worry about losing control over their data once it crosses borders. This is especially the case in regulated industries. And this fear can cause them to hesitate when it comes to fully embracing cloud services. And of course, security concerns are also top of mind. With cybersecurity threats becoming more and more sophisticated, the risk of breaches, and especially those that could expose sensitive data or intellectual property, makes a strong security measure almost non-negotiable. Confidential computing steps in to help tackle these challenges by making it easier for businesses to trust their cloud provider. The irony is that it does this by actually reducing the amount of trust that is required across all these different parts of the cloud compute infrastructure. It's designed to give you that extra layer of assurance when you're running and processing data in a cloud environment. All right, let's dive into how confidential computing fits into the current security landscape and what makes it stand out. So today we've gotten pretty good at securing data when it's at rest and in transit. Encryption of store data is pretty much standard across the board. Think Azure Storage, BitLocker in Windows, File Vault on macOS, or dmcrypt on Linux. All these make sure that when your data is sitting on a storage device, it's encrypted. Similarly, encryption of data in transit is handled with protocols like TLS, which ensures that data is safe while it's moving across a network, preventing anyone from snooping on it. But here's where it gets tricky. Data is vulnerable when it's actually being processed, when it's sitting there in the memory. This is the missing piece, something that lets data be protected through the entirety of its life cycle, even while it's in use. And this is where confidential computing comes in. It allows us to encrypt data in use, meaning you now have full control over your data from creation to destruction using a cryptographic key that you, and only you, control. This extra layer of protection can stop internal threats, like a curious administrator who might want to take a peek at something they shouldn't, or protect your data while it's running in the cloud, like in Azure. It even shields you from potential vulnerabilities in the hypervisor layer by taking that layer completely out of the trust equation. This opens the door to new possibilities like sharing data for things like federated learning while keeping that data completely confidential. Microsoft has worked with the Confidential Computing Consortium to define confidential computing as the protection of data in use by performing computing in a hardware-based and attested trusted execution environment. Those two words, hardware-based and attested, are very crucial. Attestation gives you verifiable proof that your data and code maintain their integrity and confidentiality, and it needs to be hardware-based because security is only as strong as the layers beneath it. If a lower layer gets compromised, everything above it is at risk. That's why the security needs to be baked in at the silicon level. But what does this mean for us? Well, it means that no one outside of the trusted execution environment's trust boundary can see inside or tamper with the data before it's processed. Only the code that's supposed to access the data will have access to it. If someone isn't explicitly granted access, they're locked out. The trusted computing base encompasses all of the essential components. Think hardware, firmware, and software that create a secure environment. Everything inside the TCB is crucial. If any part is compromised, the entire system security could be at risk. A smaller TCB generally means a smaller attack surface because there are fewer components vulnerable to attacks. Reducing the TCB lowers the risk of exposure to vulnerabilities, malware, malicious actors, and it can help to make your system just a little more secure. So you could say that confidential computing is there to help you decrease your TCB. Okay, so let's see whether or not we really need this. So let's see what it protects against. I'll swap to my virtual machine and I'll just open up Notepad. I'll enter some text here and then I'm going to dump the process. And then I'll use WinDebug to walk through the process's memory and extract the Unicode string that you see here on the screen. Doesn't really matter which one or which text that I enter. And it doesn't matter which process is being used. You can do this for almost any process. So I'll just use prog dump here in PowerShell and dump the contents of the Notepad process. And then we'll open up WinDebug, then open up the crash file, or the dump file, I should say. There we go. And now we could just use the address extension to display the information about the memory of the process. And I'll just use the heap filter so that I can filter to a specific memory region, and then I'll use a command, so the S command, which searches through the memory to find a specific byte pattern, and in this case we just want to print out all the Unicode strings. And if I just search for the text that I'm after, just to speed things up, you'll see that it's right there. And so this is the thing that confidential computing protects against. If you were to dump the memory contents of something that's running in a TEE, you'll just get ciphertext. So as opposed to here I can just read everything, which isn't ideal. So what are the odds of an attack like this actually happening? Who would go through the hassle of digging through a memory dump, hoping to find something valuable? Well, let me give you a recent example that you may have heard about. On July 11th, 2023, Microsoft published a blog detailing a malicious campaign by a threat actor known as Storm 0558. This group managed to target Microsoft 365 customer email systems because they got their hands on a crash dump that mistakenly contained a signing key. The key should have been protected, but the contents of the memory dump were unencrypted, and this allowed the attackers to extract the key and use it to generate access tokens using the private signing key for Microsoft accounts. Oops. But all things considered, that's a pretty scary situation. To tackle the growing scale and seriousness of all these cyber attacks, Microsoft launched their Secure Future initiative. This initiative brings together every part of Microsoft to strengthen cybersecurity across the board, from their company to their products, basically. And with this initiatives, several key security pillars were prioritized. And one of them is focused on protecting identities and secrets. As part of this pillar, Microsoft committed to securing identity infrastructure, signing, and platform keys through rapid and automatic rotation, all while using technologies like hardware security modules and confidential computing. And this is actually a pretty big deal as far as use cases go for confidential computing. The easiest way to onboard your existing applications into confidential computing is by running an entire operating system inside of a trusted execution environment. It's practically as simple as ticking a checkbox. So let's dive into the portal and see how this works. Now keep in mind that this approach gives you the most basic form of confidential computing, which encrypts the entire memory of your running virtual machine. Okay, so we're in the Azure portal, and we'll go to Deploy New Virtual Machine, and we'll just pick a random virtual machine name, doesn't really matter, it's just a demo. I don't need any availability options. The security type, we will have to change that to confidential virtual machines. And if you were to configure the security features, you can also disable secure boot if you want to. I wouldn't do that. You can also enable integrity monitoring. So if the attestation process fails during the startup sequence, this will send out an alert to Microsoft Defender for Cloud. And we also have to select a compatible VM image for confidential computing. So here I'll just filter by security type. And here, if I have the list view here, you'll see that there's plenty of options, but I'll go with Ubuntu Server. So I'll select that. And then I have to select a specific virtual machine SKU or virtual machine size. So you can only select between the DC and the EC series, and the DC series VMs that have an A in them are the AMD ones, so with SEV SNP, and the ones without are a Intel TDX powered SKU. So we'll just hit select here. Can leave all the rest running, and I should probably also enable confidential OS disk encryption. So this will actually encrypt all the critical partitions of the disk when we set this up. So if I just if I hit the checkbox here, we should be able to enable that. And this binds the decryption key to the VM's VTPM. So if you ever delete the VM object and you try to create a new one and attach it to your confidential OS disk, that shouldn't work because it's bound to your VM. And now for the other settings, doesn't really matter. Could just leave them as is. Also enabling confidential OS disk support will enable secure boot by default, and this requires all of the startup or the boot components to be signed. So drivers, kernel stuff, bootloader, etc. So we'll just create the virtual machine. I'll download the private key. I'm not going to do anything with it because from an end user's perspective, this machine operates the same way as any other machine. And you can also see this in the template. So the template, the ARM template, is mostly the same. There's a couple of properties that have to be filled in because it's a confidential virtual machine. So let's take a look. If I go to the virtual machine here, so you'll see that the managed disk has an additional property, security encryption type. And then the image reference also is different. It's a different SKU for the Ubuntu image. And then the security profile also has to be filled in. And you can find those values in the parameters file of your deployment. You can also use Bicep for this, obviously in Terraform as well. Bicep is pretty much the same deal as the ARM template that you just saw, just in the Bicep format. So let's see, the security encryption type has to be set. Security profile. And then for Terraform, it's pretty much the same thing. So if I go into my main here, the virtual machine size has to be correct. And then, the image reference and the secure boot has to be enabled, and VTPM as well. And then your OS disk encryption type has to have the disk with VM guest state value. And then you'll be able to deploy a confidential VM through Terraform. So we'll just wait until the deployment completes. It takes a bit longer than usual because of the encryption of the OS disk. But as you can see, our VM is running now. We have all the security types correctly configured. It's also configured the guest attestation extension because of that integrity monitoring flag that we enabled. And when we check the disk, you'll see that there is server-side encryption as well as confidential compute encryption or confidential OS disk encryption with a platform managed key. So even though a lot of this stuff is the same as working with any other virtual machine SKU, there's a couple of things that you're going to have to be aware of when you work with confidential VMs. A couple of limitations. Microsoft has these limitations written down on the Microsoft docs for confidential VMs. So things like Azure Site Recovery, shared disks, ultra disks, even accelerated networking doesn't seem to work at the moment. But things are moving fast, so those features might still come in a future update. So as it turns out, each CPU vendor has its own way of implementing a trusted execution environment. On Microsoft Azure, you can choose between Intel and AMD's approaches. With Intel SGX, you can run a specific portion of your code inside an application enclave. That's Intel's term for a trusted execution environment. Essentially, you have to split segments of your code base into a trusted and untrusted part. You run the bits of code that need those extra confidentiality and integrity guarantees inside the enclave. Now, inside this trust boundary, only the hardware, the firmware, and specific parts of your application code exist. Everything else is locked out and can't see what's going on. That includes the OS, the hypervisor, the cloud service providers, administrators, and also your own administrators. One downside of SGX is that it doesn't have a strong support for higher level programming languages like .NET, Golang, and others. That said, there are community projects that are trying to make it easier to run apps written in those languages inside of an SGX enclave. If you want to run an entire operating system inside of a TE, both Intel and AMD have options for that. AMD offers SEV SMP and Intel offers TDX. This approach shifts your trusted computing base significantly because now you're trusting a lot more components compared to SGX. Remember, SGX just ran a portion of code inside of a TE. You're still relying on the hardware and the firmware, but now you're also trusting everything running inside of the OS. That includes all the software that comes with the OS or that you have additionally installed. Also, all the administrators that can access that machine are now also considered to be part of your trust boundary. But remember, as before, everything running inside the TE's memory is encrypted. For example, if an Azure Data Center admin were to try and dump the contents of your running VM's memory, they wouldn't be able to peek inside and extract sensitive information. This is ideal for scenarios where you want to jumpstart your use of the flexibility of the Azure cloud while also ensuring that you're meeting compliance requirements. Let's put those trust boundaries of the two approaches side by side for a second. With application enclaves, you get a smaller trusted computing base because the security boundaries really just restrict it to the enclave. We only trust the hardware and the code that's running in the SGX enclave, after all. But with this approach, you typically need more code refactoring efforts and possibly a bit of retesting of your application. On the other hand, confidential VMs have a larger TCB, which encompasses many more components, and here you're really just putting your trust in the hardware plus the OS and software and your own administrators. So again, CVMs are much more useful when you're migrating legacy or existing applications into a confidential computing environment. For example, you can use confidential VMs to run Kubernetes workloads. This makes it easy to lift and shift your existing container images without any changes. Assigning a workload to run on a confidential VM node is straightforward. It's just a matter of adjusting the node selector or node affinity in the pod specification to target a node that is labeled for confidential compute. Having said that, though, security-wise, you'll want to go beyond just labels. Since labels can be applied to any node, it's important to implement some sort of guest attestation to cryptographically verify that the node that's running your workload is actually a legitimate confidential VM, meaning that it has the hardware-based trusted execution environment with the required security features, such as secure boot, for instance, enabled. This is achievable through the use of a sidecar container or some other method. But here's where things get tricky. Running these workloads in Kubernetes raises some additional questions. For example, can Microsoft managed control plane nodes influence our confidential worker nodes? It's worth noting that while direct memory access is prevented, control plane nodes still have the ability to control other nodes through the kubelet and provision things like daemon sets on confidential VM nodes. So using confidential VMs in AKS works for certain scenarios, but it really depends on who's inside of that trust boundary. In reality, the security benefits are somewhat limited to memory encryption of those specific nodes. So what do we do about this? We could self-host the cluster on confidential VMs. But if you're already considering a managed solution like AKS, you probably don't want the operational overhead that comes with maintaining a cluster yourself. So then what's the solution here? But fortunately, some very clever people have come together to tackle this exact problem. The idea is to take the Kubernetes layer out of your trusted computing base entirely. But how did they actually do that? This is where CoCo comes in. CoCo is short for confidential containers. It is a cloud-native computing foundation project that is designed to enable what its maintainers call cloud-native confidential computing. It works with various confidential computing hardware platforms and technologies to protect data in use. And as of now, CoCo is a CNCF sandbox maturity level. That means that it's an experimental project that has not yet been widely tested in production. The primary goal of the CoCo project is to standardize confidential computing at the pod level, which makes it easier to use within Kubernetes. This allows Kubernetes users to deploy confidential container workloads using familiar workflows and tools without needing extensive knowledge of the underlying confidential computing technologies. Confidential containers rely on a few key components, and one of them is the Kata Containers project. Kata Containers is an open source community that is focused on building a secure container runtime using lightweight virtual machines. These VMs provide an additional workload isolation through hardware virtualization technologies. With traditional containers, processes are isolated from one another using Linux kernel features like namespaces and cgroups. However, this isolation isn't absolute. You can selectively isolate resources, and if there's a bug in the kernel, it could lead to potential attacks where a process escapes its restrictions and impacts other processors or containers running on the same host kernel. Kata Containers offers an extra layer of security for Linux containers, which can be crucial for customers who find that measures like AppArmor or other host hardening techniques aren't enough. Kata uses lightweight utility VMs to run pods in containers and utilize QEMU or Cloud Hypervisor behind the scenes. If you've ever worked with Windows containers, especially Hyper-V containers, you can sort of think of Kata Containers as something similar. It's a solid choice when you need strong tenant isolation. So to recap, Confidential Containers operates on top of Kata Containers and runs an entire containerized workload within a virtual machine, which itself operates as a trusted execution environment. On Azure Kubernetes Service, you can enable Kata Containers by opting into the pod sandboxing feature. When you also opt into confidential containers, you will essentially be able to create a confidential child VM running inside of a confidential parent VM. CoCo attempts to simplify the deployment of confidential container workloads in Kubernetes while ensuring cryptographic verifiability. It comes with additional bells and whistles to make the entire thing attestable using cryptographic proofs. This way, CoCo guarantees that software runs without tampering and can even prevent workloads from starting up when it detects any discrepancies. CoCo can leverage multiple hardware TEs such as Intel SGX, Intel TDX, and AMD SEV SNP. We can even create TEs in two specific ways. We will actually be taking a look at the VM-based TE, and in this model, memory encryption occurs along a utility VM boundary atop of a virtual machine monitor. This approach uses the Kata containers runtime and the agent, with the agent being part of the trusted computing base running inside of the TE. The CoCo stack runs a Kubernetes pod inside of the VM, together with the Enclave software stack, which comprises of things like the Kata agent and the attestation agent, the confidential data hub, and other pieces of software. The container images are kept inside of the TE, and when they are pulled, they are verified and decrypted inside of the TE. Secrets like image decryption keys are securely provisioned to the TE by a trusted keybroker service, which validates the hardware evidence of the TE before sensitive information can be released. But let's back up for a second. Nested virtualization? Really? Yes, this solution uses nested virtualization, and some people might be hesitant about that. It's understandable, right? Balancing maintenance complexity and potential performance hits is a valid concern for developers and operations teams. But I've got good news for you. CoCo can be run in environments that don't support nested virtualization with the help of an extension for the Kata runtime called the Cloud API Adapter. Its job is to start Kata container VMs on any machines without the need for bare metal worker nodes or nested virtualization support. And that means that CoCo allows users to move workloads on infrastructure owned by third parties, be it cloud providers or others. As long as they have confidential compute hardware, it should work. For instance, in Azure, it involves spinning up a separate confidential VM with a specifically built virtual machine image and then designating it as a pod in Kubernetes. This might incur a slightly higher Azure bill because you're spinning up a new VM every time, but the performance gains and scalability can make this a very attractive option. What does our trusted computing base look like now? Well, it's pretty straightforward. Without confidential computing, you need to trust all components, VM admins, Kubernetes, everything. If you're running workloads on AKS with just a confidential VM node pool, you'd still have to trust the VM admins and all the Kubernetes elements. However, when you're using CoCo, the trust boundary shrinks significantly. You only need to trust CoCo's utility VM, the confidential container software stack, and the pod that runs your containers. You can enable confidential containers in an existing Kubernetes cluster using the confidential containers operator. The CoCo project provides this operator on operatorhub.io. When the installation is finished, your cluster will have a new runtime class for each of the different hardware platforms, including a generic runtime for testing CoCo without confidential hardware support, a runtime using remote hypervisor that allows for cloud integration, a runtime for the process-based isolation using SGX, as well as runtimes for TDX and SEV SNP. The primary resource is CC runtime, and this describes the runtime details. For Azure Kubernetes Service, the process involves a few other steps. To opt into the preview of confidential containers, you need to use the Azure CLI. First, you'll need to register the preview feature for the resource provider, and then you can create a new node pool for your AKS cluster using AZ AKS node pool add. The node pool must use Azure Linux, and additionally, you will need to provision CVMs that can host confidential child VMs. There is a specific SKU for this. Actually, for the moment, it seems like you'll only be able to provision AMD SEV-powered CVMs. From a tooling perspective, you'll continue to use the same tools to manage your Kubernetes workloads. The main difference is that the shim and runtime engine that handles your pod's lifecycles will be different. You can still use Containerd to run standard Kubernetes pods with the runc runtime engine, while CoCo will use the Kata runtime engine for confidential workloads. The best part is that all of this is handled behind the scenes, so you won't typically need to manage these details. If we put everything together, here's what it looks like. On the left, you have a typical Kubernetes setup where multiple pods run on a node, and you use a node selector or node affinity setting to isolate and provision workloads on specific nodes. And this can be confidential VM nodes as well. But here we have to trust the hardware platform, Kubernetes control plane, OS, other apps, our own administrators, and our application. On the right, the Kubernetes setup expands where some of our CVM nodes support confidential child VMs. But when we run containerized workloads in the CoCo child VM, this allows for a trust boundary where we only have to trust the utility VM, the CoCo software, our application, and the hardware platform that this TEE runs on. So let's have a look at how confidential containers works in a demo. So what are we going to be doing? We're basically going to be sending an encrypted message to an event hub, and then we're going to read it and return it to a browser. And we're going to return it in its decrypted form, of course. But to do this, we're actually going to be using the secure key release mechanism. And what we're going to do here is the producer pod is going to reference the public key data of our key. And then once the trusted execution environment has been attested, the key vault will return the private key to the consumer pod. So the consumer pod will be able to decrypt the messages that have been encrypted with the public key. I should also mention that as far as I know, there is no way of extracting a private key from Azure Key Vault Premium. I think it's a different story when you have a managed HSM, but at least with Key Vault Premium, getting access to the private key information only works if you do it through the secure key release mechanism. And that does require a trusted execution environment that has been properly set up and attested as well. And then we're also going to be assigning some permissions. So the producer pod needs to have, I think it has to have write access to the event hub. And then the consumer has to have the permissions to allow the secure key release to happen. And it also has to read from the event hub. So we're going to set that up using workload identity on AKS. So let's jump in. Okay, let's start in the Azure portal. I've already gone ahead and provisioned a couple of resources here. My AKS cluster, for instance, has been provisioned already. There were some capacity issues in West Europe, so I went ahead and provisioned it in East US. And so I stuck with it just to be safe. Let's see. I already provisioned a managed identity as well, an event hub namespace. And from a previous test, you can also see that I have an existing event hub, but we'll just generate a new one. Let's see. And then there's already a key vault here as well, but it's completely empty. It had a key, but it's been purged. So we should be good to go. I also don't have any permissions set at the moment. This is also something that we have to do as part of the setup process. So I have my own bit of documentation here. I expanded upon this documentation. It's actually, this demo is actually part of a Microsoft demo, part of the confidential containers demos repository. Yeah, check this out if you want. It's a really good example. The Kafka example is really nice. Yeah, if you want to tinker around with it yourself, feel free to check this out. But let's go back to my variant. It's nearly identical. Just a couple of things have been changed. So here we have the AZ AKS create command right? Like I said in the presentation, the most important thing there is the OS SKU, the VM node size, which is the CC, the confidential child capable VMs. The workload runtime has to be set to Kata CC isolation as well. And we need to have OpenID Connect, the issuer, enabled, and also workload identity. You can also use AZ AKS node pool add and create a new node pool with the exact same or many of the same parameters here. If you already have an existing cluster that you want to test with, that works as well. Then my credentials, I already have my credentials pulled here. As you can see, I have it running in K9S. So let's just start with the federated identity setup, because I've actually removed that from my managed identity. So no federated credentials are in place right now. So I'll just go ahead, provision a couple of things. There we go. And then the identity is already created, so I'll just update these variables so that we can get the client ID and the principal ID for the managed identity. And then the managed identity resource ID. I also need that because we have to set up the service account. So through this service account, we'll be able to get Entra ID access tokens for Azure resources. So the containers that we will be using, or the containers, they will be using these access tokens to access Key Vault and Event Hub. So they need a service account to do that from. So we'll just create the service account. There we go. Now, if I create the federated credential, because that's the service account is the first part, you could say, and now we need to link the name of the service account to the federated credential and the managed identity. There we go. It's been created. So if I refresh here, full refresh maybe. There we go. It should be there. That's strange. Let's see here. Yeah, it should be there. It's probably taking a while to update. Yep, there it is. Okay, so the subject identifier is correct. It's the name of the service account in the namespace, and the default namespace. And now we need to set the Microsoft Azure attestation endpoint. Yeah, we can use West Europe, even though our Kubernetes cluster is hosted in East US. Should probably change that now, just to make it look nicer. So let's change that real quick. East US, okay. So I've set it to East US now instead of West Europe. That's fine. It just means that when this T is created, it will send its attestation results to an MAA endpoint, and we will also make it so that when the key is released from Key Vault, that it actually verifies that that it has been attested against this endpoint. So it's pretty important that we set it up correctly. Okay, so the Key Vault name, I will need that. I'll also need the endpoint. So that's just the Vault URI, but without the HTTPS and then the resource ID. I also need that in this variable. Lots of variables that are being created. There we go. Now, let's just call it topic 2. Yeah, doesn't matter. Partition count 10, sure, why not? That's going to get created. Yep, it's there. And we'll export the event hub ID as well. Okay, let's see, in the Azure portal, swap. If I go to my resource group, the event hub, and then the event hub, yep, there it is, it's topic 2, good, excellent. And now we need to assign the permissions, so the read and write permissions for reading our event hub, and the Key Vault Crypto Service Release user, so that our TE is able to get the private key. Let's see. Now, both of our pods, by the way, are going to be referencing that that service account. But one of them will be running in a trusted execution environment through the Confidential Containers project, and the other one won't. So only one of them will be able to get the key. So, and you can also scope this down even further, because now I've got this RBAC assignment scoped to the key vault and all the keys inside of it. But you could scope it down to the individual key level, though I have read that that is not really the recommended way to do it, but you could potentially do it if you wanted to. There we go. Now I'll just assign the read and write permissions to the event hub. We can take a look as well. So our topic 2 should have the role assignments. There they are. And our key vault as well. There we go. Service release user. Okay. And now I need to add myself, because we have to create a key in a second. Okie dokie. There we go. That's me. Okay. Now we have to generate our consumer pod. Let's first jump into that consumer pod specification file. A couple of things to note here, right? It's using the workload identity. You have to, if you want to use workload identity, you have to set this specific label. You also need to assign a service account name. So that is the workload identity SA. Again, this one is the one that we've linked to the managed identity with federation. So it's this one in the default namespace. And then the most important one to run this in confidential containers on Azure Kubernetes Service is this runtime class. Now, this one is a bit different from the ones that you would find on the confidential containers documentation. As far as I know, the Kata CC one is only used on AKS. So Kata CC isolation as a runtime class is for Azure Kubernetes setups. We can even search for it, and you'll see that, yeah, my blog is there as well. But yeah, it's typically used for for Azure setups. So you won't find it anywhere else, in case you're wondering. Okay. And then we will also be using the sidecar, the SKR sidecar. So that's for doing secure key release from Azure Key Vault. Basically, the consumer container is going to call into the sidecar and it's going to request the key to be released. And then the sidecar is going to hand off the private key from Azure Key Vault to the container. And then it's gonna run. We also have a couple of environment variables, and these have to be replaced, but we will do that in a moment. And I believe this file is needed. Yeah, this mount is needed for the SKR image. Okay. So let's replace the some of the stuff in the consumer pod specification. So I actually have to run this in the Kafka directory because it's looking for that consumer YAML here. So let's see what has changed. So as you can see, it's filled in the container images there for Microsoft. Kafka demo pipeline. Yes, that's the key that we will be using. So this is a key ID. It picked up the MAH endpoint that we changed. Okay, so everything seems to be in order here. We can almost run it, so that's good. There's one more thing we need. We need to generate the security policy. Remember, there is a part inside of the confidential containers setup that requires us to create this security policy. And when the VM actually starts, the utility VM, it's going to check this policy. And if the policy doesn't match, the container, the pod rather, will not be started. So it has to match. It's actually a Rego policy that will be generated. In order to do this, you need to use the AZ confcom extension. So you can install it with this command. I already have it installed. Let's see. This is going to pull the container images and do some calculations as well. Okay. And with that out of the way, we should have, we should have the policy here. I should probably open that up here. Okay. Disable line wrapping. Okay. So the policy is basically a very large open policy agent policy that's been base64 encoded. So if you wanted to, you could take a look and see what this is actually all about. And now we will actually be creating the key that we will be using for the rest of the project, let's say. And one of the things for this key is it will use a secure key release policy. And all of the values inside this policy have to match the evidence that is provided when you do the key release. So this is why we calculate the workload measurement of the consumer file. As you can see, it will be hashed as well. And so every time, if you were to change anything about this file, it would be picked up and you would not be able to release the key. But I will show this in a moment. Let's just generate the key first. Let's have it generate. Okay, there we go. So the key has been generated, and I'll just show the value here of the workload measurement. So let's copy that. So basically that's the hashed base64 decoded policy. So if I go into the key vault, this will make a lot more sense when we actually take a look at the key. Look at the Kafka demo pipeline key, you'll see we have one version here. It's marked as exportable, so that means that if a trusted execution environment requests it, it can be exported to the trusted execution environment, provided that it matches the confidential operation policy. So let's take a look at the policy. So all of these properties have to match, right? So when you request the key from Azure Key Vault now, and you provide the evidence, it has to be attested by this endpoint of the Microsoft Azure Attestation Service, so the shared East-US endpoint. The TEE must be running inside of an SEV SMP VM. There's also a bit of host data, which is arbitrary data, and this is actually our workload measurement that we calculated. So if you were to change the YAML file, this wouldn't match anymore. So, and then there's also this additional check. Let's say it has to be running inside of a Kata CCU VM, so the utility VM, and the trusted execution environment has to be running in a non-debuggable state. Basically, those are the things that it has to match before the key is ever released. Okay. And so now we could actually already create the file, I think, if we wanted to. Let's just do that. Let's just skip this part of the part where we generate the producer pod YAML and just deploy kubectl create f consumer. There we go. If I take a look now with K9S, you'll see that the container is creating. So it's been assigned to the node pool, which is good. Still creating, so it takes a while for the thing to start up. And it's running. Okay, so that's good. We can take a look at the SKR container. You'll see that it's actually it's running in debug mode for some reason. Doesn't really matter. There has been one request to perform a key release. So that's probably the other consumer container. It will actually not output any logs for some reason, but that's okay. It's running. There's also a service, I think, that's been created. So if I were to use this external IP, I should be able to see, well, not much because we haven't produced anything. But the private key is now inside of that pod, basically. Okay, so that's good. Let's create the producer. There we go. Let's see what we've changed here. The public key, okay. And then the event hub namespace and the event hub itself and a log file. So again, with this one is going to create messages or events, I should say, and it's going to encrypt them with the public key. And so we're only going to be able to decrypt it with that private key that's been released to that other container. So if we do another kubectl create f producer swap over pods. Okay, this one is actually running. Again, this one isn't running in a trusted execution environment. It's just a pod, a normal pod, let's say. So it's already running. This is good. I think if I refresh the page, I don't think there's an auto refresh on this. So there we go. So the message is there. Now if we swap back, I've installed an extension here by not an official extension, but it doesn't really matter for the demonstration purposes, which will let me view the contents of an event hub. So let's just quickly connect to it. So event hub, select event hub, my enterprise subscription, and then the second topic. And if I start monitoring, it's created the partition. Okay, and there you go. That's all of the messages that have been sitting there in their encrypted format. If I hop on back, if I refresh, I should still be able to see all these messages in their unencrypted form. So yeah, there we go. One final thing that I want to mention is that even though all of this looks very cool and works without any problems whatsoever, it's always a good idea to check the limitations of the technology that you want to use. And for confidential containers on AKS, it's no different, right? There's a couple of things that you need to consider when you want to use this. There's also some limitations and some behavior that you're going to want to be aware of, like this one, for instance, with the resource limits. But I think all of this stuff should become more easier to use in the future once the technology matures. So just so you know. So what about confidential AI? NVIDIA is already taking steps towards making sure that they have support for running confidential AI workloads through the Confidential Containers project. They have a technology preview available of their NVIDIA GPU operator that comes with support for CoCo. The NVIDIA operator uses the operator framework within Kubernetes to automate the management of all the NVIDIA software components needed to provision the GPU. The technology preview lets you test some basic workloads, but it's still early days on this front, as there are still plenty of limitations in place. For instance, from the looks of it, it only seems to work with their H100 GPUs at the moment. And even if you were to get your hands on one of them, these GPUs are available to containers as a single GPU in pass-through mode. Multi-GPU pass-through and vGPUs are not supported right now. You might have already heard that Microsoft has announced that Azure will support confidential AI workloads. More specifically, this will be achieved through combining capabilities of the confidential VMs with NVIDIA's H100 GPUs. From the announcement, it said that these VMs are ideal for training, fine-tuning, and serving popular open source models such as Stable Diffusion, its larger variants, and also large language models. But unfortunately, I couldn't get access to them. The NCC ADS H100 V5 series VM SKU appears to be in private preview. This means that I'm unable to share detailed information due to the non-disclosure agreement that's associated with the preview. And that's too bad, of course. However, you can still perform some light CPU-only AI inferencing using confidential containers. Microsoft has an impressive demo that showcases confidential inferencing on Azure container instances with CoCo. This demo uses the NVIDIA Triton Inference Server, which has been specifically built for CPU-only inferencing of Onyx runtime models. And on the client side, the Triton client library and sample code can demonstrate how to set up a test TLS between the inferencing service and a client application. I believe it should be possible to adapt the setup to run on AKS, so it's definitely worth exploring. Microsoft is doubling down on confidential computing, as they believe their services need to get to a point where confidential computing is the default mode for computing. They're doing this by supporting developers with tools to help them make confidential computing more accessible, as well as providing customers with confidential computing-enabled versions of popular services. For example, Databricks or Azure SQL. So let's end with a couple of key takeaways. Confidential computing is here to help you overcome cloud adoption challenges, where you'd need to have private data center guarantees while still having the flexibility and scalability that a cloud platform such as Azure offers. As far as lifting and shifting containerized workloads go, AKS is a good fit for running confidential workloads. Just figure out how much trust you're willing to place in the infrastructure provider. And based off of this, you could opt to use something like confidential containers in case you simply cannot trust anyone but yourself with your workload. Just remember that CoCo is still a CNCF sandbox project, which makes it an experimental project, meaning that it may not yet have been widely tested in production setting. CoCo also runs on Kata containers, which requires nested virtualization, but can also work in peer pods mode, which allows the container runtime to spin up separate confidential non-nested virtual machines for you instead. This allows you to essentially run your workloads confidentially in anyone's cloud, as long as they provide confidential computing hardware and a means to perform attestation. I've been exploring various aspects of Azure Confidential Computing and documenting what I've learned along the way. This blog is my attempt to break down these concepts for anyone that's interested. Writing everything down helps me to understand how these technologies work. And I'm also focused on figuring out how to provision these components using infrastructure as code, which some people might also find very useful. So feel free to dive in and learn alongside me. That wraps it up for me. I hope you've learned something valuable, and I appreciate you taking the time to listen. If you have any questions or you want to explore these topics further, feel free to reach out, and I'll see you later.